All right, so we're in chapter 3. We're plugging through quite a bit of material, and we've even introduced the quality, the property of the quality, the enthalpy. We looked at projections of the PVT surface. Last time I mentioned this, that the subscript F is used, let's say V sub F and U sub F, for the saturated liquids specific volume or internal energy. And I mentioned it comes from the German root word in thermodynamics, and because of the English we would have moved to L, but L is confusing. It's easily confused with number 1, and so L is a bad subscript in general. And so this is the German word. I looked it up for what a liquid is. So there's their meaning. And G like V sub G and U sub G, that's for gas, and that means like a vapor in English. So gas is a word in German as well, GAS. And it means just like it means in English. I mentioned in an email that I was interested in having some people develop STL files, and then we print them, some small PVT surfaces. A couple people responded. If you're one of them, thank you. I'll probably suggest, if they talk to me, or if you talk to me, to truncate the plot right here instead of taking it down to 0. But I'd like to have some people generate some STL files using SolidWorks, and we'll send it off to I already talked to Dr. Hahn about this. He said no problem. He's in charge of the 3D printer in the mechanical engineering office, and we'll print them. Probably make some holes, probably on the back side and the back side there, and then make it where it's a void, and otherwise it'll be a solid block. He said it doesn't matter if it's solid or if it's a void, but maybe I think about 3 or 4 students have responded, and so they're going to give it a shot. It'd be nice to do that. Then I could pass around. Then I could have the student hold it in their hand and then look down the axis for the projections. That's my goal. All right. This plot, the pressure temperature plot, I really encourage you to think about, spend some time on, because now we're going to talk about the thermodynamic tables. And a lot of times students don't know which table to get into. Should I be in the 2-phase table that deals with that liquid vapor transformation, the boiling, condensation? Should I be in the subcooled liquid table? Should I be in the superheated vapor table? Or should I even be in the 2-phase solid vapor table right in here? Well, a lot of times this plot will help you determine it, because you'll know something about the temperature and the pressure. So if I know the temperature and the pressure, and maybe I plot it and it goes like, oh, there it is, then I know, oh, I'm in the vapor region. Maybe I plot it and the pressure temperature shows up there. Well, then I know I'm in the liquid region. Or if it shows up precisely on the line, well, I'm in the 2-phase region. And there's a couple ways to look at this, because this plot, this line, is from the triple point to the critical point. You talk about either the saturation pressure as a function of temperature, looking like this, going this way, up and across, give me the pressure. I give you the temperature, you give me the pressure. Or you could do it like this, the saturation temperature is a function of pressure. That would be, give me a pressure, and I'll come across and give you a temperature. And so a lot of times what you do is you say, well, I'm given a temperature and a pressure. Maybe I'll compare this pressure with the saturation pressure for the given temperature. It may sound confusing to you, but that's what you're going to end up doing a lot of. And you'll say, oh, the actual pressure is greater than the saturation pressure at the temperature. Okay? If the pressure is greater than the saturation pressure at that given temperature, maybe I'll erase this and show it on the diagram. It's like, take this temperature. I know maybe the pressure is right here. I get the saturation pressure. There's P sat. There's the physical pressure, P. and P is greater than P sat. Isn't that what I said in equations? I'm in the liquid phase. Or what happens if it comes back and it says, oh, the pressure is not greater, it's less? I'm in the vapor phase. See how you kind of test that? Do the same thing if you said, okay, let's do temperature, pressure, and now let's compare the saturation temperature for the given pressure. And then you compare these two, this physical temperature that you're given plus the saturation temperature. And so let me erase all this and try it again. So here is my given pressure, and I come out and I get the saturation temperature, T sat. If the physical temperature T was greater than, so maybe I got that in the way, put this over here, T is greater than T sat, then it's superheated vapor. Or if T is less than T sat, then it would be something like, well, I should have plotted it along the same line of pressure, shouldn't I? Stay on the same line of pressure going across. If the temperature is less, hey, it's in the liquid. You have to do that yourself. I know I may make it look easy, but I know a lot of students struggle. Like, how did you know that it's compressed liquid, or how do you know it's superheated vapor? Okay. So there's a lot of these tables that we have to get into and work through. This one we already covered. Why is there not a chemical formula for air?
Mixture.
Because it's a mixture, but we'll treat it as if it's a pure substance for a lot of cases. Why is there not a critical temperature, critical pressure for carbon? It's primarily a solid. It's not a gas. These Z critical, we'll get to it, compressibility factor. Notice they're all about the same at the critical point. All right. Here was a question I think I gave last time. Let me give it again this time as a clicker question. So, I'm interested in water. I'm interested in V sub F. What is the name of V sub F? The specific volume of saturated liquid. It's the saturated liquid specific volume at a temperature of 100 degrees C. Okay? Is that value, if I told you, go get me out of the table V sub F for water at 100 degrees C, the saturated liquid specific volume, what value would you come back with? Value A, B, or C? Let's go ahead and see if we can't get 100% correct on this. Yes, this is the temperature right here of 100 degrees C. Yes, this specific volume is all right here. Saturated liquid, V sub F, right there, that's correct. Okay, now last time I tried to emphasize this. When you get up to this point, what is the name of this point? The last entry in that table A2. It's either the triple point or the critical point. It's the critical point. It's a very high pressure, 22 megapascal or 220 bar. Temperature around 374 degrees C. Right? Okay. When it goes to the critical point, is there a difference between the saturated vapor and the saturated liquid specific volume, or are those the same? At the critical point, Cp, is V sub F equal to V sub G? Yeah, it is. So these two values should be the same. True? Are they the same? They are the same. So that helps you interpret the meaning of this header right there, V sub F times 10 to the 3. So what it says is they took the physical value of V sub F, multiplied by 1,000, took that result and stuffed it in a table. So when you want the value out of the table, you take the physical value out of the table, let's say 3.1555, and don't multiply by 1,000, divide by 1,000, or multiply by 10 to the minus 3. And then that will be the physical V sub F. that you use. And now we see, oh yeah, that interpretation of this is in agreement. Those now, sure, I take this number out, divide by 1,000, and it is equal to B sub G. It's okay. So does that help you if I ask this question again? Let's ask the question again. So the second clicker question, I'll go back and grade the first one after I grade this one. So at 100 degrees C, what is the value of V sub F? All right. So do you think we're 100% correct as a class? It's pretty rare to have 100% correct. Oh, well, what happened to E? Yep, somebody selected E. Well, they didn't want to allow me to have 100% correct. All right, so I don't know what happened to E. But there you go. Now let's go back to the first question and look at that. We are improving. Right? We moved from 68% correct to almost 100%. All right? So there you go. Here's another question. What is the triple point pressure? Triple point. Yeah, what is the triple point pressure? The numbers shown on this here plot. Is it 6.11 millibar, 0.00611 kilopascal, 611 kilopascal, or 0.0611 megapascal? And we'll go ahead and take your answers. All right. Well, this question highlights why they helped, they put up this little convenient unit conversion reminder for pressure. So I encourage you, you have access to the tables during the exam to really become familiar with that little unit conversion factor up there, because they like to give this in bar. But then there's so many units of pressure, you just have to become familiar with it. So if I look at it, isn't this the pressure that I'm interested in? Isn't that the triple point pressure? Yeah, it is. So I wish the answer would have been given 0.00611 bar. You'd have said, there it is. But we changed it up a little bit, made it hard. Well, what's a millibar? Yeah, so this is another way to write that, 6.11 times 10 to the minus 3 bar. True, like a millimeter is 10 to the minus 3 meters. A millibar is 10 to the minus 3 bar. Hence, 1, 2, 3. Correct answer, A. But why do we only have 50-some% correct answer? Because you have to get real familiar with pressure conversions, okay? We don't see millibar often. We see kilopascal, bar, megapascal, atmosphere, a lot of other pressure units. So please just get very familiar with pressure unit conversions. All right. There's a couple other things that I need to point out on this. Let me jump to this slide. It's reference states. Energy, especially internal energy and enthalpy, they're energy, like kilojoules of energy per kilogram of mass. We're interested in changes in energy. You think about it a little bit, it's not like the total energy is a meaningful number. We talk about processes, we talk about the change in the energy. That's how much heat came in or work was done, that changed the energy of the system. So we're interested in that, changes in energy, so that the beginning of the energy measurements cancel out in the calculation. So if I had U2 is equal to some U plus some U reference, and then I had, well, this is U2 plus some reference, then I would, when I had the minus U1, the two references would cancel in the equation. So for water, this table is based on setting the internal energy of saturated liquid at the triple point to a value of 0. So there you go. Professor, could I have a negative value of U? Could there somehow be a negative value of U? Would it be meaningful to have a negative value of U? And the answer is yes, there would be. Could I have water that is maybe at negative 20 degrees C? Now you ask the question, it's probably going to be ice. Am I going to have to transfer energy into the ice to get it up to be, let's say, saturated liquid at 0 degrees C or 0.01 degrees C? Yeah, I probably have to transfer some heat in. That's going to bring up the internal energy. So you can find U's, we'll go look at them in the tables for water that are negative, and that throws students for a loop. But that's just where they set the value. They set it saturated liquid at the triple point is 0 for the energy measurement. Notice that the enthalpy is just a slight amount greater, and it's due to U plus PV is H. And so this is 0 at that triple point for saturated liquid. You need the saturated liquid pressure, the saturated liquid specific volume, do the product, the units work, and that's why you get slightly greater than 0, 0.01. All right. Now, I want to talk about enthalpy column for a minute. They gave us a saturated liquid value, they give us a saturated vapor value, and then they gave us this value in between, and they called it evap. What? HFG. What? Okay, do this. Take a system that has saturated liquid in it. All right, so it starts at saturated liquid, and let's say the mass is 1 kilogram. And you apply some, bring some heat into the system, Q. During the process, you're bringing in heat until the end of the process. I still have the mass of 1 kilogram because it's a closed system. The mass hasn't changed. There's my system. I'm focusing on that trapped amount of water, that 1 kilogram of water, but it's now all saturated vapor. Okay? The weight of the piston didn't change. Did the pressure of the water change during that heating process? Frictionless piston, the elevation of the piston went up, but the weight didn't change. Does the weight depend on elevation? You know, I'm standing on the floor, I weigh so much. If I stand on the table, does my weight change? Do I go to the top of the room? Is my weight different? Weight's independent of the elevation. The weight of the piston is independent of the elevation, hence the pressure of the gas under that piston is independent of the elevation of the piston. So it could expand at constant pressure, true? It expanded at constant pressure. So what you do is you write a first law for the process. We brought in some heat, we did some work, and we changed the internal energy of the system. I'm neglecting changes in kinetic and changes in potential energy. Do you like that first law? Okay. This is all on units of kilojoules. Because I have a trapped amount, let's put it on a per kilogram basis, and I know I'm thinking about 1 kilogram. So lowercase q minus lowercase w is equal to the change in lowercase u. That's all kilojoules per kilogram. It's all on a per unit mass basis. All right. The work is the boundary work. Isn't that the integral PdV? Constant pressure boundary work? That's equal to P times V final minus V initial. Or it's P2V2 minus P1V1. True? I mean, P1 and P2 are the same. So when it's convenient, I'll say it's P2. When it's convenient, I'll say it's P1. So what we find with a little algebra is Q is equal to U2 plus P2V2 minus U1 plus P1V1. You know what? The amount of heat brought in to take the 1 kilogram of water from saturated liquid to saturated vapor is exactly H2 minus H1, or Hg minus Hf. It's the difference between the saturated liquid specific enthalpy and the saturated vapor specific enthalpy. See that? And so this is so often used that they added a special column right here called HFG, and HFG is simply defined as H of G minus H of F. That's all. And it has an interpretation of being the amount of heat needed to vaporize, to take from saturated liquid to saturated vapor, that 1 kilogram of fluid at that pressure. They'll also, you could, and some books do have UFG, which is use of G minus use of F. It's nice to have, but it's an extra column and it's not as needed or as often used as HFG. And they also will even have V sub FG, which is V sub G minus V sub F, as well as when we get to entropy, SFG. But basically, most textbooks only put in the difference between the enthalpy, the saturated liquid, saturated vapor, because it has such a clear interpretation. It's the amount of energy per unit mass to boil or vaporize that fluid at that pressure, constant pressure. So there you go. That's why that column is a little wider for the enthalpy. You have saturated liquid, saturated vapor, but you have this additional HFG column. Now, you have the pressure table. So A3 is if pressure is the most convenient input to it. And so that's very convenient. Notice that 1 bar is about 1 atm. It's not precisely, hence the boiling point is not precisely 100 degrees C. But the boiling point temperature, the saturation temperature is 99.63. Notice that they did not give, and that's just the choice of the authors, they did not repeat the triple point. But they did repeat the critical point. I don't know why. If I was the editor, I'd have said, put in the pressure table, repeat the triple point. Okay? They just left it out. Notice, what is the HFG at the critical point? Because there's no difference between the V sub G and the V sub F, nor the U sub F and the U sub G, nor the H of F and the H of G. There's no distinction of boiling at the critical point. All right. So when you look at this pressure temperature diagram, the information in table A2 and A3 is basically the same information. It's just what is the input? Is it temperature input or pressure input, the most convenient parameter coming in? That covers all of this data from the critical point down to the triple point. That's tables A2 and A3. Then what about table A4, properties of superheated water vapor? That's out in this region. That's table A4. How about compressed liquid? That's out in this region, table A5. And then saturated water, solid vapor here. That's table A6. Why don't they give both the temperature and the pressure? Too many tables. They could have reformatted that data and given just like a pressure table for that two-phase region, but they didn't. Well, let's take a look at table A4 for the superheated region. Everything is in what we call pressure blocks. This is a pressure block. Everything in here is for this pressure of 0.7 bar. And because so many unit conversions associated with pressure are so tedious and error prone, they tell you, oh, 0.7 bar is also 0.07 megapascal. True? Can you do me a favor? Can you tell me how many kilopascal this is? If you get those three down, you're 90% of the way. You won't get tripped up in pressures. Jump between bar, megapascal, and kilopascal. How many kilopascal is it? 70. Very good. Very good. All right. Here's another pressure block right here, and it's 1 bar, 0.1 MPa, or how many kilopascal? 100. Very good. So now, take a look at all the data in here. They have a temperature column. So typically, you're given pressure, temperature, go get specific volume or internal energy or enthalpy. And so you would say, oh, it's 280 degrees C, it's 0.7 bar, I'm looking for the internal energy, U, in units of kilojoules per kilogram. That's the value I need. You grab it and roll. Okay. Why do they stop this table? Well, they could keep going, but usually the applications for steam, aren't too many where it's a lot higher than 500 degrees C at those pressures. Okay. The next thing is this a temperature? They call it SAT. What are they doing there? Well, that value is this temperature right there. So the first row in that pressure block is for a temperature of 89.95 degrees C, which is the saturation temperature at that pressure, right? And so basically, if you wanted to, you could look at these numbers, and they're going to be the same numbers. It's going to stitch together in the other tables for the saturation tables of water vapor, liquid vapor, I mean. Okay, so you could go and double check those, and they'll link up. Okay. Now, this pressure block over here has a different saturation temperature, doesn't it? But these are the saturation values for that temperature. Now, one of the things they did was they didn't repeat the, I don't know why, but they could have easily put 100 here, 120 there, and a SAT there. But they didn't. So you kind of have to look and say, what is the temperature for this one right here? You got to look over, and it's right there. I know they didn't save much ink, did they? I wish they would have just repeated that column. But they didn't. So you have to know that these temperature values here go all the way across even for the next pressure block. There's 2 pressure blocks side by side. That's the format of this textbook. Now, table A5, compressed liquid. Okay, there's some compressed liquid there. It's put in pressure blocks as well. Notice they have the 10 to the 3 up here. Liquid's very dense. Okay, so if I wanted to know the specific volume of water, H2O, at 2.5 megapascal and a temperature of 80 degrees C, what number would you give me back? Don't on an exam, please don't. You won't get a lot of partial credit. Just put 1.0280 meter cubed per kilogram, right? I'm looking at this value right here, right? What number should I put? So 0.001028 meters cubed per kilogram. And think about it a little bit. That's a little bit over a liter per kilogram. That makes sense intuitively. Yes, sir.
How would we solve problems where the pressure is significantly less than 25 bars? Like one of the homework problems.
Okay, a couple approximations that we'll use is when it's not very high pressure and you need U, just go get it as a function of temperature, the saturated liquid value as a function of temperature, and neglect the effect of pressure. The same with V, and the same with H, and the same with S. Okay, so all the properties. You would just say, look, it's not a tremendously high pressure, go get the value. Approximately, it's the saturated liquid's value at that temperature, neglecting the effect of pressure. That reflects that you're reading the book and solving homework problems, which I applaud. Thank you. Any other hand up? I thought I saw another hand up. All right. Notice they also tell you at that whopping pressure, here's the saturation temperature. So you can use this to check and say, hey, they gave me a pressure of 2.5 megapascal and they gave me a temperature of 80 degrees. Well, guess what? That 80 degrees is significantly less than the saturation temperature. It's subcooled liquid, it's cold liquid, it's compressed liquid, different terms for it. It's liquid. It's liquid. Okay? All right. Okay. What about this table, A6? A6 deals with saturated water, solid, vapor. True? And it's just a temperature input. Notice that the temperatures go down. This is very cold, so it's ice. Let's take a look at negative 20 degrees C. Can I have ice or water at negative 20 degrees C? Yes, you can. It'll be, you'll have to heat it up before it starts to melt, typically. Okay. So, unless it's at this pressure, that's the saturation pressure, very low pressure. But take a look at these internal energy values. Notice that for the saturated solid, what are some signs of these? They're negative. Remember what I mentioned about, hey, you could have a negative U. You could have a negative internal energy. That just means your datum point is higher than the actual condition. And the datum point for water was set saturated liquid at the triple point is 0 for the internal energy. So here, yes, you do have negative U's. All right. Let's take a look. So this is from the solid to the vapor region. If you go back to that 3D PVT surface, you'll see that two-phase region. This one, you need the tables. If you have tables, can you get them out, please? What is the state of water at 10 bar and 240 degrees C? Is it solid? Is it liquid? Is it vapor? What is it? Is it a two-phase liquid-vapor mixture? Is it a two-phase solid-vapor mixture? This type of games you need to play often. Do we have enough tables that how many students can do this problem? Not enough hands? Well, so I won't do it for a clicker question then, but what you want to do is you go to some of the table and let's say I think about the pressure is known or given to me, okay? Great. 10 bar. Go and find the saturation temperature at 10 bar. Okay, so I'll go to the table. There's 10 bar right here. I find that its saturation temperature is 179.9 degrees C out of table A3. Then I compare the actual temperature given. It's 240. I compare it to the saturation temperature. What would you conclude? I'll ask that as a clicker question. All right. Well, did you still working on it? Sorry, you got to watch that time. It is in the vapor region because the physical temperature, 240, is greater than the saturation temperature of about 180. Superheated vapor, higher temperature than saturated vapor. So here's another question. So we're talking water. We're talking 10 bar. 240 degrees C. What is the value of U? Well, you'd have to go into the tables and get it. But I would go into the superheated table. I would get to the pressure block of 10 bar. And then I would come down and find a line of 240 and then just read it off, okay? All right. What is the state of water at 5 megapascal, 180 degrees C? Well, 5 megapascal is how many bar? Five megapascal is, it's at 50 bar. And if you take a look at 50 bar, we find that it's the saturation Tsat at 50 bar is 264 degrees C. So the physical temperature is 180. Let's redeem ourselves. Let's do this one. You got 30 seconds only. All right, so let's take a look and see how we responded. Liquid it is. It's true, it is liquid. Well, the 180 is lower than the 264. So at that tremendous pressure of 5 megapascal or 50 bar, it's colder than the lower temperature than the saturation temperature. So it's liquid. It's somebody may say, well, how do I know it's not so cold that it's solid? If you have a good visual image of that pressure temperature diagram, you kind of come up like this. I'm emphasizing the change in slope there. And water kicks back like that, right? What's the maximum temperature for ice? For solid, maximum for water, maximum temperature for water to be solid. Triple point. Everything below that, 0.01 degrees C, is not a. It's you can have it to be when it's less than 0.01 degrees C a solid, but you can't when it's greater than 0.01 degrees C. It's impossible. Your two choices are you're either going to be a liquid or you're going to be a vapor. True? There's no way to have 180 degree C water that's solid. It's just not going to happen. All right. Oh boy, do I want to do another one of these? Sure, why not? Yeah, or skip it. Do you want to skip it or not? Do it? All right. All right. What is the state of water at 10 bar and 180 degrees C, or 179.9 degrees C? So what we do is we say, let's go look up the saturation temperature at 10 bar, and we find, 179.9 degrees C. That's the same value. Well, you tell me what your best estimate is. I have water 10 bar at that 10 bar and that temperature. What is it? All right. Well, because this was precisely the same temperature to 4 significant digits, we would say, aha, if the temperature is the saturation temperature, it's somewhere in that two-phase region. Somewhere in that two-phase region. Somewhere in that liquid-vapor two-phase region. And so that's the correct answer, D. Now, somebody says, well, then I'm going to want to get an internal energy as a function of temperature, pressure and temperature that's in that two-phase region. Are one of these values going to work? It could be anywhere between u sub F and u sub G. Temperature and pressure are not independent properties in two-phase region. I need another property. I would need some other property, let's say U is a function of pressure and quality. Or maybe I know the quality. If I knew the quality, I could get a numeric value. So the correct answer for this question would be you cannot determine it just knowing the temperature and pressure and it's in the two-phase region because they're not independent. Okay. Linear interpolation, do a quick review. So you go back and you have a generic x-axis, y-axis. You have a point right here, x1, y1. You have a point right here, x2, y2. And if I want to find the y value for an x in between, so x between x1 and x2, I want to get that y value. That y value will come in between y1 and y2. And what you do is I like to think about what is the fraction of the way going between the lower value to the upper value. So that fraction of the way would be x minus x1 divided by x2 minus x1, wouldn't it be? Visibly, I'm looking, maybe that's around 20% of the way. F would be about 20% as I've shown it. Then guess what this fraction is? The same fraction. It's 20%. That's linear interpolation. So y here, that value of y, would equal y1 plus y2 minus y1 times that fraction that I moved. So y1 plus y2 minus y1 times x minus x1 divided by x2 minus x1. Sometimes we own these equations. We need to own linear interpolation at this point in our career. So sometimes you're given this. You say, I need to get the internal energy at this pressure and that temperature. All right, you come in, you say, oh, that's superheated vapor. So you go to the right pressure block. It's the right pressure block. And you march down the temperature column and you go, oh, no. They don't get, I wish they would have given me this temperature to be something like 80. Then I just pick the value off and away I go. But you have to interpolate. And so at this point, I would encourage you to say, you know what, I need to interpolate between 36 point, is that 1/6? My eyes are a little bad today, and 80. Right? I need to do that interpolation between those two values to get this u value. And that u value, when I get it, it better be between the upper and lower limit of 2425.0 and 2487.3. Okay? So let me just let you know that you can do this interpolation. I encourage you to do that interpolation. The fraction of the way, I like to bust it into two steps. I like to get a fraction where it's 50 minus 36.16 divided by 80 minus 36.16, which is about 3141. About 31% of the way between the lower value and upper value. That's how far it is. And then I use that fraction to get u is equal to 2425 plus that 2487.3 minus 2425.0, the difference times that same fraction, that 31%. And so the answer for this comes in right around 2444.57 kilojoules per kilogram. If you're needing that for subsequent calculations, keep all of those digits. If that's the final answer, round it off to 4. Round it off to 4, u is equal to 244, let's say 5 kilojoules per kilogram. Call it quits. You'll never lose any points rounding off to 4 digits, especially on data like this. All right? Any questions about that? Double interpolation. What? That makes this other interpolation look easy. Sometimes you're given a thing that says, I'm at this pressure, 20 kilopascal, and 95 degrees C. You conclude, oh, I'm out in the superheated region, superheated, okay? So I take a look and I say, uh-oh, they give me 6 and they give me 35. So this pressure right here, whoops, I need to get there, is equal to 6 kilopascal. This pressure is 35 kilopascal. I need 20 kilopascal. Not only that, they give it to me at 95 degrees C. Both of these, they have it at 80 degrees C and at 120 degrees C. What do I do? Bust it into 2 steps. Interpolate with respect to one of them first and then the other second. So make maybe a 20 kilopascal pressure, a new table for 20 kilopascal, and then get a value for 80 degrees and 120 degrees for whatever we're interested in. In this case, we're interested in U, isn't it? Aren't we interested in U? And so I worked this out, and the 2 values for U are 2485.562 and 2543.59. And then I do the second interpolation between those two, going from 80 to 95 degrees C between the two. And so you do 2 interpolations, and the final answer is, I'm going to write it down here. Well, I'll put it right here, 2507 kilojoules per kilogram. All right? 2507.3. Now, I think you have all the tools to do that. You just need to do it. Also, Emmanuel as well as Savannah can answer any questions on this. All right? Oh, I didn't cover as much as I wanted to, but I have finished with my time. Thank you for your attention.